Okay, so we're doing rates of change. The derivative that we've been finding throughout this whole topic is a rate of change. On a graph, it is the gradient that measures the rate of change, which is our derivative. And the rate of change of the dependent variable with respect to the change in the independent variable. In other words, the rate of change of y with respect to x. Okay, that's how we write our derivative. Suppose that a quantity q is given as a function of time t, as shown in that little diagram that's there. There are two types of rates of change that exist. So the first type is the average rate of change. This is the gradient of the line segment between 2 points. So it might be the population of rabbits at time 1 grows to the population at time 20. What was the average rate of change? So you want to know those 2 points, and you want to find the gradient, because gradient is rate of change. And there is our good old-fashioned 2-point formula to find the gradient. Okay, that's all it is, gradient between 2 points. The other type of rate of change is the instantaneous rate of change. This is the gradient of a tangent at a particular point. And we've been doing lots of this, hopefully. You should have been doing lots of this, okay? To find the tangent, we always find the derivative, dq over dt, and then we substitute the x value of the point where it touches the curve. Sounds familiar, hopefully? We are going to classify rate of change. So if you see those words in a question, you are going to classify that as an instantaneous rate of change. You're going to find the derivative and you're going to sub into it, okay? Unless it asks for average rate of change, specifically, we're going to use the derivative, okay? When we study a curve, we can find points where the gradient is increasing. Increasing is where the tangent slopes upwards from left to right, or decreasing where it slopes downwards. Now, to see this, you just need a ruler, okay? So you can see if I put my ruler and make some tangents on that side of the curve, all those gradients are sloping downwards. They are all negative gradients. And as I bring my ruler down, bring it around the bottom of that curve, once I hit the turning point, I now have a flat ruler or a horizontal gradient, which means a gradient of 0. Okay, then as I keep following my curve, it now is spinning around the other way and I have positive gradients. Do you get the idea? Positive gradients to the next turning point. Okay, here are our examples. A cockroach plague hit the suburb of Erina last year, but it was gradually brought under control. The council estimated that the cockroach population, which is called P, in millions, T months after the 1st of January, was given by the equation P equals 7 plus 6t minus t squared. Okay, part A. Differentiate to find the rate of change. Okay, it's even told you to differentiate, but we see those words rates of change, which means we know we need to differentiate. We're differentiating equation that is a p equal, so it's dp, and our independent variable is t, so it's dp over dt. So just treat it like we would a y and x equation, but it's the t's where we're looking for the powers, okay? The 7 is a constant. It will disappear. The 6 is next to t, so the t will disappear, and I'll just get a 6. And the minus t squared, I bring the 2 down. It'll be minus 2, subtract 1 from the power, will just be t to the power of 1, or t. So that is the equation for the rate of change. It's the derivative. That's all it is. Part B. Find the cockroach population on the 1st of January and the rate at which the population was increasing at that time. Be careful with the units, it says there. So first of all, notice the date. 1st of January, and up here, 1st of January. Okay, the 1st of January was the starting point of when this data is been calculated. Okay, so what we're doing there is we're subbing in when time, or t, is equal to 0. Now I want to find the population, which is the P. So my P equation highlighted in yellow, the 7 plus 6t minus t squared. I just want to sub in that t is 0. So that's 7 plus 6 times 0 minus 0 squared. But obviously that is just going to be equal to 7. Here's the units part where it said be careful with units. What is the units of that P there?
Millions.
Millions. And it would be million cockroaches, yes. So it is in millions. And we're talking about how many million cockroaches we have. Okay, now we also want to find the rate, which was dp over dt at the start. What is the rate of change of those cockroaches at the very start when time is equal to 0 still? We are subbing that into the equation that I found in A. So that's going to be 6 minus 2 times 0. 2 times 0 is nothing. So that is 6. What's the units? 6 million cockroaches per what? It is month. Good. So we know that the unit on the bottom, it's a dp is the population. That's my 6 million. There's 6 million cockroaches. And the dt, t stands for time. So I need to know the units of the time, which it says where t is in months up here in the question. Okay, so it's 6 million per month at the start. Okay, we know that rates of change can change, but at the start, the cockroach population was increasing by 6 million cockroaches per month. Part C. Find the cockroach population on the 1st of April and the rate of change at which the population was increasing at that time. Okay, so remember we started on the 1st of January and we're counting in months. We're going to the 1st of April. How many months? 3. So we now want to go when t equals 3, and we want to sub that into both of our equations. Same two equations. So p equals, or if I shrink it down, you'll be able to see it. There it is. 7 plus 6t minus t squared. So that will be 7 plus 6 times 3 minus 3 squared. I think that's 16 million. Okay, so we started off at 7 million. Our cockroach population has grown to 16 million. What about the rate? The dp over dt. What's happening with that? Subbing into the equation in A, we get 6 minus 2 times 3, which equals 0. So that was an important point to find because that's actually when the growth of the cockroaches is actually stopped. Put a halt on it, okay? So that is units, remember the units? So 0 million per month. Okay, so we must have done something. They've got the population under control a bit there. They've stopped it from growing. Part D. When did the council manage to stop the cockroach population from increasing any further, and what was the population then? We kind of already know that because it happened in the last question. But assume that we didn't do C. If we didn't already know that we'd managed to stop it at t equals 3, if you were trying to find that, you would start with when the dp over dt equals 0. Okay, so it says, when did they get under control? When was the growth rate stopped? It would be when that dp over dt equals 0. And we already had that, so it's going to come out as the same answer. It was dp over dt is 6 minus 2t. That was the equation. And that's equal to 0. Solving that, I get 2t equals 6. And there's my t equals 3 again. And it would be 3 months to include the units. It does say there, when did they manage to get the cockroach population under control? That's the 3 months. And what was the population then? 16. We already know. It's a bit of a double up here. So what's the population again? So let's just repeat that. when t equals 3, we already know that the population is equal to 16 million. I won't sub it in again. We already worked that out before. Part E. When were the cockroaches finally eliminated? Eliminated means population of 0. No cockroaches left. So when p equals 0, into the original equation, I have 0 equals 7 plus 6t minus t squared. It's a quadratic. I don't like the t squared being negative because that makes it hard to factorize. So move everything to the other side so that it's positive. T squared minus 6t minus 7 equals 0. Then we're factorizing, so we're looking for two numbers that times to give minus 7 and add to give minus 6. Minus 7 plus 1. So t minus 7, t plus 1 equals 0, which means that we get t, using the null factor, t equals 7 from the first bracket, or t equals negative 1 from the second bracket. However, given that this is a practical situation, can t be a negative number? No. So we put a little note here saying that this is not a solution for that second one. Okay, so maybe just over on the side. Therefore, cockroaches were eliminated after 7 months. Okay, so that t equals 7. F. What was the average rate of increase? See those words? Average rate of increase. We've talked about that at the theory part at the beginning. Not the instantaneous rate, the average rate, which means I want the gradient between the 2 points. Okay, so from the 1st of January, so we're using t is what our x variable normally is, and the p is our y variable, right? So 1st of January was when time equaled 0, and my population was, do you remember? Or look back at 7, good. So when time equals 0, the population was 7. On the 1st of April, t was what? 3, and the population was 16. So there are my 2 points. So my rate is going to be using the y2 take y1 over x2 take x1, subbing in. So subtracting the y values, 16 take away 7 over subtracting the x values, 3 take away 0. 16 take away 7 is 9, and 3 take away 0 is 3. 9 divided by 3 is 3. Now this is a rate. What are my units going to be? It's million, that's right, per month. Part G, where it all comes together. It says draw the graph of P and dp dt, so there's two graphs here, as functions of time, and state their domains and ranges. Add to your graph of P the tangents and chords corresponding to parts B, D, and F. Okay, we'll try and put all of this on a diagram is what it's asking us to do. So first of all, okay, kind of divide that space in half because you've got two graphs here, okay? So I'm going to start with the graph of P, which had the equation, I'll write it down, it was 7 plus 6t minus t squared. Now we're drawing this graph. What type of graph is it? It's a parabola. What do you know about the parabola? The negative in front of the t squared means it's going to be concave down. Very good. Okay, so that's important to recognize from the start. We also know that we're not going to be using any negative time. So we're only interested in the first quadrant.
Y77.
Yeah, very good. Oh, not x, it's t versus p. I've already got a p up there, so I'm going to leave that one there. So at the very start, that was my next question. Thank you, Lachlan. When time was 0, our population was 7, remember? So I'm going to have, I'm going to go up by 2s here, because 2, 4, 6, 8, 10, 12, 14, 15. Okay, so time is 0, my population is at 7, right there. Okay, through all the other parts of the question, maybe look back at part C, we also worked out when time was equal to 3, didn't we? What was the population at time equals 3? 16. So let's go 1, 2, 3 across here. Actually, I might need to make those smaller because I need more space than that. So 1, 2, 3. So at time equals 3, the population was 16. Is there any other bits of information that we calculated already? We're not looking at the gradients yet, this is just the population. When was the population 0? At 7. So down here, after 7 months, because remember time was in months, after 7 months, the population of cockroaches was 0. That time equals 3 is important as well because it's the turning point. Okay, the reason we know it's the turning point is because that's when the rate was 0, because we know it's coming up, it stops, and then it's going to come back down. So we've actually got enough information there to draw our parabola. So it comes up to that turning point, down to that 7. I was asked to find the domain and range of that. This is good practice for people finishing their logo. So domain, X is, not X, T. It's normally X, but T. For this particular question, what is my domain?
Greater than 0.
It kind of has to be between two things. I know normally a parabola could keep going between 0 and 7 because I can't go into a negative population, so it's not going to go down further. I can't extend it any further down there, and I can't go into negative time. So between 0 and 7 for my time. The range, which is normally my y values, but it's going to be p.
0, 6.
Yeah, my smallest one is 0, and the highest was 16. Very good. Okay, while I'm there, before I go on to the second graph, just for this graph, it says add to your graph of P the tangents and chords corresponding to part B, D, and F. Now, B was when time was equal to 0. Okay, so with a ruler, if you have one, or a straight edge of some kind, you want to draw, it asks for the tangent. We want to draw the tangent at that point. I'm going to use blue. Okay, so it's a bit tricky to do when that's kind of the edge of our graph. But what we can see there, this is for B, that the rate of the population at that point is increasing quite steeply. Okay, that tangent's quite a steep gradient there. Part D was the time equaled, it was when time equaled 3, because it was finding when the rate was equal to 0, which is going to be right up the top, my turning point. Okay, so that one's for D. F was my average rate, which would be a gradient joining between the 0, 7 and the 3, 16. Because it's where you go between the 2 points. It's going directly from there to there. That's what happens when we do an average rate of increase. That's what that line represents. Okay, we only have to do that for the P graph, but we do need to draw a second graph, which is our derivative. We want to sketch dp over dt. We know the equation was 6 minus 2t. What type of graph is that? Straight line. Good. Very good. It's good to know that from the start. So let's draw up a Cartesian plane. Do I need negative parts for my dp over dt?
Yes.
Yes, it can. You can have negative rate, and we actually do in this question. I still can't have negative time though. So t is there, dp over dt is my y-axis. And again, this is going to be over the same 7 months. So when time was 0, looking back to part B, when time was 0, what was the rate of change? 6. So my dp over dt intercept is at 6. 2, 4, 6. I'm going to put it right there. Okay, let's look at part C. When time equals 3, my rate of change was 0. So at time equals 3, my next point is there, 0.
There you go.
Sorry?
Straight line.
It is, it's going to be a straight line.
Yeah, right. So you just need 2 points.
We do, well, yeah, but we know it has to end at 7. So let's find out what happens at 7. Okay? So we didn't actually calculate this in any of the other parts, but when t equals 7, because we know it has to end at time equals 7, the dp over dt equals 6 minus 2 times 7, which is negative 8. Okay, just so you can see it's 7, where I'm going to try and rig this to look like a straight line. Down here at minus 8. Okay, and rule that one up. Did I make it look straight? Yeah, pretty good. Okay, we still need the domain and range. Yep, so domain, we're talking about the t values are between 0 and 7, just like for the other graph. The range is the dp over dt. The smallest value is negative 8. Good thing we worked that out. And the highest value is 6. So between negative 8 and 6. I know it looks a little bit funny having a dp over dt in the middle there, but that's what our y-axis is. All right, that is the end of that question, but there's still another one. I'll let you finish writing. I'll see if you people are still frantically writing that down. All right, question 2. The graph to the right shows the temperature T of a patient suffering from Simmons syndrome at time T hours after her admission to hospital at midnight. Okay, that kind of is a key thing there. They were submitted at midnight. Important to note that. When did her temperature reach its maximum? So you can see on the graph, the highest point on the graph is when little t is equal to 3. Okay, so it's going to be when little t equals 3, but we could also write that as a time because we know what time she was admitted. If she was admitted at midnight, 1, 2, 3 a.m. Part B, when was her temperature increasing most rapidly? Let's do that one before I read the second half. Increasing most rapidly. So remember, that is talking about the rate at which it's increasing, the tangent we're talking about here, the slope. So if I grab my ruler and it says increasing, I'm not interested in all those negative gradients on the other side of that turning point there. I just want to know on this side of the graph, where is it the steepest? As I come up to that turning point, it's actually getting shallower and shallower, isn't it? So it's going to be the steepest right back here at the start. Okay, so her temperature is increasing the most when time equals 0. So increasing the most, or I should say most rapidly. That makes better English, isn't it? Increasing most rapidly at t equals 0, which in other words is midnight. The second part of the question says, when was it decreasing most rapidly? I'm going to write that question down first. So decreasing most rapidly. Okay. Yes, so we're now looking for, as the curve is coming down the other side of that turning point, where is it going to be the steepest? So it's going to start off nice and, very small negative gradients, and it's getting steeper, 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 until I get to that point there, when time equals 6, and then it starts getting shallower again. Okay? So that point, which we call a change of concavity, so it was coming down and then it kind of changed and went back up again, that is where it's going to be decreasing the most rapidly. So time equals 6, in other words, 6 a.m. And there's even another part, when was it stationary? When it's at that turning point, which is when time equals 3. So stationary at t equals 3, or in other words, 3 a.m. Can you read that? No, that's a bit small. What happened to her temperature eventually? So as, she's gone to the hospital, her temperature is increasing rapidly. They must give her some medicine maybe, who knows, but her temperature stops increasing and it starts decreasing again. But, no, she doesn't die. Okay, don't be dramatic.
Stationary.
It approaches, like it's coming down to like an asymptote there, isn't it? It's coming down and it's stabilizing at whatever that constant number is there, which makes sense. You hope that her temperature is coming down to the 36 or 37 degrees, which is your normal body temperature, and will hopefully stabilize and stay normal there. So what happened was her temperature, it stabilized at a constant temperature. The graph doesn't tell us what that is, but it's a constant temperature. Part D, sketch the graph of the rate dt, d capital T over d little t, so capital T is for temperature, little t is for time, remember, at which the temperature is changing. So we are just drawing one graph in here, just the rate one. Now the time, because we've already got the time one there up in the top corner, what's happening in there is happening over 9 seconds. So we're going to keep that same scale for the t axes. So 3, 6, 9. Yeah, Ashton?
Will we need a ruler for the test?
Not really. It's just, all the graphs are still, I'm still sketching them freehand. The scale, just trying to think if there's any other point you'll need. I don't think you'll need a ruler. No, you can just do them freehand like this. Next week. Okay, that's time axes. This is going to be the d capital T over d little t, the rate that we're sketching. We know that the rate is 0 where?
At 3.
Yeah. Wherever there is a turning point, which is this point here, wherever there is a turning point, it's going to be going through 0. I'm going to change colour so you can see it better. It's going to be going through 0 on the rate graph. Now we know originally that her temperature is quite high, positive temperature, but the rate at which it is increasing is going to start to slow down. Remember that? So it's starting positive and it's going to be coming down to that 0. So it's going to be starting positive rate, but slowing down to a 0 rate. Then it has a negative rate, which means that it's decreasing. Her temperature is decreasing, the rate of the, between 3 and 6, because 6 is the point, that point of inflection, right? And that becomes a turning point on this graph. It comes here, it's going to turn around, and then it's going to come up and approach a constant, like an asymptote there, a constant steady line as it goes across. As in, the rate is leveled off. So, yeah. Do you know what I mean? Okay, so that is what the rate of change looks like. So let me just summarize that. Okay, let me just do what I just did. A 0 on the original graph. So this 0 means a 0 on the rate graph. So turning point, the turning point becomes a 0 down here. The point of inflection means that it's going to turn around because it's going from being a concave down graph to a concave up graph. So that means a turning point down here for your rate graph. Okay? And then just because this was leveling off, it had to just level off after that. Yeah, it's new. Okay? But they're the key things. So the last part, Tori, you're right. When was the rate of change decreasing? This graph is the rate of change, right? It is decreasing from time is 0, it's coming down, decreasing all the way down to 6. Okay, and then once it gets to 6, it starts increasing again. So from 0, time equals 0 to 6, it is decreasing. Which in other words is midnight to 6 a.m. From t equals 6 onwards, it is increasing. Which is 6 a.m. onwards. Okay? And we need to do 9J.